One day, Mr. Bedney was in his backyard setting up his homemade rocket. When he set off the rocket, it took off in the curve of 0.5x squared. After the rocket took off into the sky, Mr. Bedney never saw it again. To try to find his rocket, he wanted to calculate the area that the rocket traveled between 1 and 4. Solve using 6 rectangles. So our equation is y equals 0.5x squared between 1 and 4. Today we are going to be walking you through how to solve this problem using 3 methods.
The area under a curve is the area of a function above the x-axis on a specific interval. We must first begin by setting up sigma notation. Sigma notation is an expression that represents the sum of an argument over a specified integer range of values. For example, this problem would be read as the sum of 0.5k plus 1 squared times 0.5 from 0 to 5. To solve sigma notation problems, you must expand the argument, plug in the variable, and solve.
The symbol that somewhat resembles the letter E is called sigma. The number on top of the sigma and the number on the bottom of the sigma are known as the indices. The top number is the ending point, and the bottom number is the starting point. The equation next to sigma is the argument or expression that explains how the area under the curve is progressing. Sigma is used in math as a shorter way to indicate sums. This symbol is used to represent the addition of a long list of numbers or terms. The equation made through sigma notation represents the total area under the curve, meaning the base multiplied by the height.
There are 3 ways to solve for the area under a curve: right endpoint rectangle, which slightly overestimates the area, left endpoint rectangle, which slightly underestimates the area, and trapezoid, which is the closest to the actual area. Now back to our problem. The problem says to examine the curve between 1 and 4, and to use 6 rectangles.
In order to find the base of each rectangle, we will subtract 1 from 4, because in between these two numbers is our specified interval, which is equal to 3, and then divide that number by the number of rectangles, which is 6, to equal a base of 0.5.
Next, we will set up notation beginning at x of 0. We will add 0.5 each time because that is the base of the rectangles. Because we started at 1, the height of the equation has to be 0.5k plus 1 squared. That number times the base, which is 0.5, gives you the area under the curve.
Now on to how to find the area using left endpoint rectangles. As mentioned earlier, this will be an underestimate, but will give us an idea of the area. I'm going to break this curve up into 6 rectangles with the left corner touching the curve.
I am first going to label the base of each rectangle as 0.5, the base that we previously discovered. Now I'm going to label the x-axis with all of our values from the summation notation x sub 0, x sub 1, etc. that we figured out earlier.
The height of these lines will be the f of that value, so I'm going to plug that value at the base of the line that touches the curve into the equation we created. This will give me the height. Then I will multiply the base of the rectangle, which we already established was 0.5, by the height that I just found. This will give me the area of the rectangle. I am going to continue this for the remaining rectangles.
Now that I have found the area of each rectangle, I am going to add them together. This total is an underestimate of the true area, but it gives us a pretty good idea of the area under the curve. And that's how you find the area under the curve using a left endpoint rectangle.
Now on to the right endpoint rectangles. Like before, I am going to draw 6 rectangles, but this time I am going to have the right point of the top of the rectangle touch the curve. The base of the rectangle is still 0.5, even for right endpoint rectangles.
The value associated with the side of the rectangle that touches the curve is what we are going to plug into our equation. To find the area, just multiply the base values by the new height values, starting this time at x sub 1. And that's how you find the area using right endpoint rectangles.
Lastly, we will find the area using a trapezoid. I am simply going to separate the area under the curve into 6 sections without forming rectangles. As you can see, the shape that this creates is a trapezoid. Next, I am going to label the x-axis in the same manner as the left and right endpoint rectangles. I am going to find the height in the same manner as before, but this time I am going to plug both values associated with the sides of the trapezoid connecting to the curve into the equation.
Now that I have found the first 2 heights, I'm going to do this for the rest of the trapezoids. Okay, so the equation for finding the area of a trapezoid is a little different than simply base times height. The equation is 1/2 times base 1 plus base 2 times the height.
Next, we plug the two bases, which we would have previously called heights, into this equation and multiply it by 0.5, which was our base before, but has now become the height. This will give me the area of the trapezoid. Now that I have found the area of each trapezoid, I am going to add them together. This is our final answer. The trapezoid offers a more accurate estimation of the area under a curve because it includes the triangles that are cut off from the underestimate and does not contain the extra triangles on top of the curve that the overestimate has.
Thanks for watching.